Hi, physics people. I am just checking in here with the continuation of our waves PowerPoint from last cycle. I'm going to just skip through the first few slides or run through them and start where we left off. Okay. So we talked about last cycle waves, vibrations of waves. And let me just advance to the next slide. There we go. The time of a back and forth swing of a pendulum is called the period. That's a little review. We talked about all of this, the types of vocabulary to describe a wave, the troughs, the crests, the amplitude, the wavelength, the frequency. We measured in hertz, how to find the frequency, how to find the period, a little math involved. Wave motion. We talked about the electromagnetic spectrum. We talked about how energy is transferred by a wave. No matter is transferred between the 2 points. The stone in a pond moves the disturbance, not the water. And this screen, I think, is new to you guys. So notice how the energy moves, not the material itself. Isn't it mesmerizing? You're getting sleepy. You're getting sleepy. LOL. Okay, so what is a medium? So when someone speaks, the sound wave is a disturbance in the air that travels across the room. The air molecules do not move along. The air is the medium through which the wave travels. Okay, so the medium is what is the wave traveling through? That's called the medium. So we have transverse waves. They move at right angles to the direction of the wave that is moving. So if you take the string, you tie it to a doorknob, and you shake it up and down, it's going to create a transverse wave. And it moves in right angles to the direction in which the wave travels. Example, a rope shaking up and down. Longitudinal waves. Longitudinal wave is if particles oscillate parallel or along the direction of the wave. Sound moves compressions of air parallel to the source. So sound waves move longitudinal. Wavelength, that's the distance between one crest to the next or one trough to the next. You see the bunched up parts are the compression parts right here and here. And we call rarefaction are these more spread out parts. Okay. Interference. This is an important term that we're going to be talking about this week. Drop two rocks in water. The waves produced by each other overlap and can form an interference pattern. An interference pattern is a regular arrangement of places where wave effects are increased, decreased, or neutralized. So here, this section in the middle here, that's where interference is taking place. Constructive interference is the crest of one wave overlaps the crest of another, and their individual effects add together. So constructive is adding together. Okay, notice in the picture. Okay, and then we have the result is the wave of increased amplitude called reinforcement. Destructive interference. The crest of one wave overlaps the trough of another, and their individual effects are reduced. Here are the waves, and then this is their effect. Okay. Reduced. The high part of one wave fills in the low part of another, called cancellation. Interference is a characteristic of all wave motion, whether waves are water waves, sound waves, or light waves. Standing waves. A standing wave is a wave that appears to stay in one place. It does not seem to move through the medium. Standing waves, certain parts of a standing wave remain stationary. The nodes, you can see here, where it passes through the equilibrium, that's called the node. Okay, and then the antinode is down at the top or at the bottom. The positions on a standing wave with the largest amplitudes are the antinodes. Antinodes occur halfway between nodes. The incident and reflected waves interfere to produce a standing wave. The nodes are places that remain stationary. So notice where it's stationary right here along the middle. That's where the nodes are. Okay. You can see right here in this picture of the waves. Notice the middle parts. Those are the notes. So A, we have half a wavelength. B represents one wavelength. And then C would be 1.5 wavelengths. So this one, that represents a half. This one is one full. And then this one is 1.5. Okay. Wave speed. The speed of the wave depends on the medium through which the wave moves. Whatever the medium, the speed, wavelength, and frequency of the wave are related. If the wavelength is 1 meter and 1 wavelength per second passes the pole, then the speed of the wave is 1 meters a second. This formula we introduced last cycle. I think it was one of the last 2 days of last cycle. I gave you a thing to fill out, and I think there were 3 problems you had to solve using the formula. V is the wave speed, velocity. This lambda, it stands for wavelength. It's a Greek symbol. And F is the wave frequency. Example, the most annoying sound in the world has a frequency of 10,343 hertz. The speed of sound is 340 meters a second. What is the wavelength? So remember, we'd have to go back to our formula. We'd go back, we'd do V equals lambda times F. We're looking for the wavelength, so we'd have to actually divide. All right, so I guess the answer is not coming up here, but let's see if I'll go back and do the actual calculation. Let's watch that again while I'm calculating. 343 divided by 340. So if you got 30.42, that would be meters because we're talking about wavelength. You got the correct answer. And I did that by taking the division. Again, looking at your formula, filling in what was missing. Whoop. Okay, so here we have a chart here. Wavelength and frequency vary inversely to produce the same wave speed for all sounds. So keep in mind the inverse relationship, that's that opposite relationship we've had all year where one goes up and the other one will go down. Notice this column, the 340 stays the same. And the frequency, as the frequency goes up, notice what happens to the wavelength. The wavelength goes down. Or vice versa. You could say the wavelength is going down, the frequency goes up, and you have the same wave speed. And that's it for now, folks. Look for follow-up lessons and follow-up notes later this week. Thanks. Bye-bye.